Okay, let us start. Uh, Good evening, everyone. This week we will start week 10 content, and in this we solve four questions related to the one question related to the determining the relay damping matrix and the damping coefficient or the damping coefficient corresponding to the particular mode. If we have the damping for the other mode, so what will the damping to the corresponding to the and different mode, and then we will go into the uh, force vibration of the multi-degree of freedom system, in which we will solve three problems, which will be related to the finding out the displacement, base shear, and the movement, etc. Okay, so let us start. In this first example, the properties of three-story shear building are given in the figure. If mass is 4500 kg and the stiffness K is given as a 300 kilonewton per centimeter, derive a relay damping matrix such that the damping ratio is 5% for the first and second mode. So what we need to compute, like the first we have to compute the relay damping, and then the second we need to calculate the damping ratio for the third mode. So for this, first we need to find out, like in the multi-degree of freedom, first part is to generate the mass matrix and the stiffness matrix. So for the, and then we will need to find out the eigenvalue, eigenvectors. So which will we need, which will do the needfuls, because in every multi-degree of freedom we need the modal frequencies. So for that we need to calculate the mass matrix and the stiffness matrix. So can you do a try, like what will the mass matrix for this, this is the degree of freedom 1, 2, 3. Okay, so the mass matrix would be the, like these I have discussed earlier, because if you will do by yourself, that will definitely help you to calculate these things. So mass matrix here, first I have find out what is this, m 0 0 0 m 0 0 0 m by 2, and I am take up the m outside. So this is my mass matrix. And for the stiffness matrix, let us suppose this is my k1, this is my k2, and this is my k3. Okay, so the stiffness matrix would be the k is equal to k1 plus k2 minus k2 0 minus k2 k2 plus k3 minus k3 0 minus k3 and k3. This is the stiffness matrix, like in which we need to put the values of, like what would be the k1, k2, k3. So here like I will write the terms, like let us suppose I will write this as a 3k, that would be the 7k, and that would be the 9k. Yes. Because if I will write k by 9 as a k dash is equal to k by 9. So I simplified these terms, so that would be help in the, that would be help us to calculate the different like the to solve the equation, which will definitely help us. So I write it at k by 9 as a k dash. Okay, so that is a 3k dash, 7k dash, 9k dash. If I will put this value in the, what will be my k1 is the 9k, k2 is the 7k, and k3 uh, is the 3k. So if I will solve the equation, I will put these things into the equation, into the matrix. What will be the my matrix? That would be the this one, like k1 plus k2 would be the 16k, these two would be the 16k dash. Okay, these k2 plus k3 would be the 10k dash, and last k3 is a 3k, and this is the matrix. Now after that we need to find out what is our eigenvalues and eigenvectors. So for this, we need to determine the eigenvalue problem. So k minus lambda m, determinant of the k minus lambda m should be 0. So for this, if I have right, there is maybe network problem. There may be some network problem today. So I will, okay. So we restored our network. So after that, eigenvalue and vector. So if we put the uh, k minus lambda m. So what was the our m matrix? That was the 100,000,000.5, okay, times m. So I have put it lambda. So that would be some lambda, and the k and m I have like keep it aside to easy to solve this equation. So if I solve this, so I will get the uh, equation. The polynomial equation is this. After rearranging the terms, my polynomial equation is coming out to be this: minus lambda cube by 2 plus 16 lambda square minus 124.5 lambda plus 189. And if we solve this equation, we will find the three roots. So these three roots are the: lambda 1 is equal to 2 k dash by m, lambda 2 will be 9 k dash by m, and lambda 3 is 21 k dash by m. So what would be our k dash? K dash is k by 9, okay. And what is our k is given in this equation? That is a 300 kilonewton per centimeter. So if we can write it as a 300 10 raised to power 3 into 10 raised to power minus 2 newton per meter. So that will become as a 300 10 raised to power 5 newton per meter. So it will be 30 into 10 raised to power 6 newton meter. And mass is given up as a 4500 kilogram. Okay. So we find the natural frequencies by putting these values. Omega 1 is comes out to be 12.17 radian per second. Omega 2 is coming out to be 25.81, and omega 3 is coming out to be 39.44 radian per second. Okay. So after that, we calculate the like the relay damping matrix. What will be the our relay damping matrix? So that will be coming out to be with the, you do know what is the equation for the relay damping? So that is the C is equal to alpha m plus beta k, where alpha is the coefficient of mass proportional damping, coefficient of mass proportional damping, and beta is a coefficient of stiffness proportional damping. So we need to first find out the for the relay damping we need to calculate the alpha and beta, because mass matrix and the k we have already. So for calculate the alpha and beta, as I have written, like alpha is the mass proportional coefficient and the beta is the stiffness proportional coefficient. So now these coefficient can be calculated from the damping equation. So damping equation in the nth mode is given as a alpha by 2 omega n plus beta by 2 into omega n, where alpha and beta, as I have discussed earlier, and omega is the modal frequency corresponding to that nth mode, and xi n is the damping ratio corresponding to the nth mode. So like if you have read in the NPTEL, so this way of damping is given. This is the mass matrix, mass damping. This is the stiffness proportional damping. So for this we have to calculate the, this is the xi omega. So this relationship comes from there. So for like we have given the damping for the first and the second mode. We have given the damping for the xi 1 is given as a 5%, xi 2 is given as a 5%. So for the we can write this equation as a xi 1 is equal to alpha by 2 omega 1 beta by 2 into omega 1, xi 2 is equal to alpha by 2 omega 2 plus beta by 2 omega 2. Okay, so we have two equation, two unknown, so we can find out easily. Okay, so for this, for mod 1, for the first mode, xi 1 is equal to alpha by 2 into omega 1 plus beta by 2 into omega 1. And for this, if I will write, if I will write if I will write put the values 0.05 alpha, omega 1 is given as a 12.17. So this is the one equation. Okay, for the mode 2, same equation, whatever I have write for the mode 2, xi 2 is equal to alpha by 2 omega 2 plus beta by 2 into omega 2, and I put the values of damping. So that is coming out to 0.05 is equal to alpha by 2 omega 2. What was over omega 2 is that 25.81, and that is a 25.81. So if I put these and solve these equation, both of the equation 1 and 2, then I find that my alpha and beta is coming out to be, alpha is coming out to be 0.827 and beta is coming out to be 0.002632. Okay, so after getting these alpha and beta, I will put these into the relay damping matrix equation. That was this. So now I have alpha, mass, and beta and k. So if I will put the values of the alpha is the 0.87. This is my mass matrix. This is my beta value, and this is my k matrix, and that is the k dash value. Okay, that is my k dash value. And if I solve this equation further, I get the damping matrix as a this one. This metric damping also symmetric damping matrix in the Newton second per meter. So this is my part A. Now in part 2 or part B, I have to determine the damping corresponding to the third mode. So the damping ratio for the third mode, like as you know, we have discussed xi n would be the alpha by 2 into omega n plus beta by 2 omega n. Now I know my alpha, beta. So corresponding to damping, corresponding to xi 3 would be the alpha by 2 omega 3 beta by 2 omega 3. Okay, and if I will put the value of alpha and beta and omega 3, I will be able to find the xi 3. Okay, so this is the expression which I have discussed. Xi n is equal to alpha by 2 omega n plus beta by 2 omega n. So for the third mode, xi 3 is coming out to be alpha by 2 omega 3 plus beta by 2 omega 3. So when I put this equation, I get this my damping ratio as a 6.23%. So this way I find out the damping matrix and the damping ratio for particular any mode if I haven't I have know the damping ratio for particular, like for the calculation of the damping ratio for any other modes. We need to first like determine the damping ratio for the, we need to know first two modes or any other one. There is no necessary like first two modes should be known. Like that can be happen with, if I know that omega 1 and omega 3 or xi 1 and xi 3, then corresponding to that we can calculate the xi 2. Okay, now this is the question to the force vibration. So in this you need to, we need to calculate the force vibration corresponding to this. In this, a two-story frame with the floor masses and the story stiffness is shown here. The structure is subjected to harmonic force Pt is equal to P naught sine omega t. Pt is equal to P naught sine omega t at the top floor. Derive the equation for the steady state displacement of the structure by the model analysis. Okay, so for this, uh, first we need to determine the steady state displacement. Like the force at the top floor is applied at P naught sine omega t. Okay, so for this case you also need to first formulate the mass matrix, formulate the stiffness matrix, and then find out the eigenvalue, eigenvectors, and then we will able to find out the our like the steady state displacement of the structure. So let us discuss it with one by one. So first the mass matrix. Mass matrix would be same as the m1 will be the mass, like this is the degree of freedom 1 corresponding to 1. This is the degree of freedom corresponding to 2. Okay. So the mass matrix is coming out to be m0 m by 2, and the stiffness is given k and k, same for all the story. So the stiffness matrix become as a k1 plus k2 minus k2 minus k2 and k2. Okay. So that would become as a 2k minus k minus k k. Okay, so the stiffness matrix is become as a 2k minus k minus k k. So I need to find out the first what is by eigenvalue and eigenvector. So for this I have determined the eigen equation, like k is the determinant of the k minus lambda m should be 0. So for this I have put 2 minus lambda minus 1 minus 1 1 minus lambda by 2. Like I simplify these, like taking the k, like that equation, are you thinking like this should be like that, 2k minus lambda m minus m minus 1 k minus lambda by 2 into n. So I have taken some sort of k is outside or lambda is outside, or I know already what would be the lambda means for me. Omega lambda something would be like in the final answer, that would be the k by m, some coefficient alpha, and if I will put it, then it can replace it with the alpha. If you want to replace it with the alpha, then you can do it, but this is the simplified method. With this I solved it, and after solving this equation I get the lambda equation for the polynomial 2 2 degree of polynomial. And if I solve this equation, I get the lambda 1 and lambda 2, which is 2 minus square root 2 plus, and the lambda 2 is equal to 2 plus square root 2, or that will be the k by lambda multiply also. Okay, k by m. So corresponding to these lambda 1 and lambda 2, I need to determine the mode shape. Okay, because for the displacement and all the multi degree of freedom, mode shapes is very important. So first we need to determine the mode shapes. So for that, first we like resolve this equation, omega 1 and omega 2. So these are like taking the square root of this, taking the square root of this. In this, that is the 2 minus, this is the coefficient, and this is k by m. K by m, and that is the 0.765 square root k by m, and that omega 2 is same, like we have taken the square root of this. So omega 1 is coming out to be 0.765 square root k by m, and omega 2 is coming out 1.848 square root k by m. Okay, so now after this I will go to the mode shift. So for the first mode, lambda 1 is equal to 2 minus square root. So what is my matrix? Like what was the matrix? K minus lambda m. That was the 2 minus lambda minus 1 minus 1 1 minus lambda by 2. So if I will put lambda 1 is equal to 2 minus under root 2, what will become my equation, my matrix? That would be the lambda 1 is the 2 minus under root 2 I have put. And if I solve this equation, that multiplication with the eigenvector 511 by 21. So in this 511 is the mode shape corresponding to the first mode, first degree of freedom, and 521 first mode corresponding in the second degree of freedom. So this last subscript corresponding to the mode, and first subscript corresponding to the degree of freedom. Okay, so if I simplify this matrix, I get this matrix square root 2 minus 1 minus 1 1 by square root 2 511 521. So I can write this like, let us take first equation. So the first equation will be the under root 2 511 minus 521, that is 0. So if I consider like normalize, or the like I consider 521 is equal to 1, so what will be my 511? This will be the 1 by under 2, and if you solve this 1707. Okay, so this way I get this equation. Like if 521 is the 1, then 511 is coming out to 0.707. Now same way I need to find out the mode shape corresponding to the second mode, which is lambda 2 is equal to 2 plus 2 lambda. So now this equation will change, like in the minus place of the minus I will replace it with the plus, and the whatever is the changes in this equation is coming out to be this. Like only these diagonal elements are changing. So for this I can write again the equation minus under root 2 512 minus 522 is equal to 0. So if 522 is 1, 512 coming out to be minus 1 by square root 2. So that is also coming same, but in the opposite direction. 522 is 1, then 512 is the, sorry, that would be the 512. Okay, that is the minus 0.707. So after getting these mode shapes, I will determine the generalized properties of the multi-degree of freedom system. So the equation of motion for the single degree of freedom system mu double dot ku is equal to pt, you know, and the displacement vector on the multi-degree of freedom is shown as the ut is equal to summation of n, like n is equal to n 0 to n phi n qn, and the equation of motion for the multi-degree of freedom system is given this in the in terms of the qn, this qn. So Q1 is a model response actually. So Mn, Qn, Kn, Qnt, Pnt, where Mn, Qn, and Pn are the generalized properties. Mn is the generalized mass, Kn is the generalized stiffness, and the Pn is the generalized force. So how to determine the Mn? Mn is the phi n transpose mass matrix into phi n. This is our Mn. How to determine Kn? That is a phi n transpose stiffness matrix into phi n. And how to determine the generalized force, that is the phi n transpose into pt force vector. Okay, so let us find out one by one. So first mn, we have 2 degree of freedom, so we would have 2 mn, like m1 and m2, k1 k2 p1 p2. Okay, so this way we find out the mn, kn, pn. So m1 is the phi 1 transpose m phi 1. So m phi 1 we have get the value as a, like what was our vector of the mode shape, that was a 0.7071 and minus 0.7071, mode shape 1, mode shape 2. Okay, So here first for the m1 we use the first mod set phi 1. So after calculating this we get the m1 is equal to m. For the m2 we also got the m. Okay, let's put this value of the phi 1 transpose phi 1, and this is the mass matrix, and if you solve this equation you will get the m. Same for the generalized stiffness k1 k2, that is the phi 1 transpose k phi 1, phi 2 transpose k phi 2, and in this k1 you will get the 0.586k, and the k2 is the 3.41k. So after getting this m1 m2 k1 k2, I need to find out the generalized force p and p. So first I need to find out the what is my pt vector, this, because still I haven't find out the pt. So for the pt, so pt is given as a, like in the question they have given, like the only the force is applied at the top of the story, or that was the p naught sine omega 2. So my vector pt would be the 0 for first story, and that is the p naught sine omega t for the second story. So if I need to calculate the generalized mass p and t, so for the p and t, like I will calculate the p1t is the phi 1 transpose into pt, and phi 1 transpose is what, that is 0.7071, and what is pt, 0 p naught sine omega t. So if I solve this I will get this equation 0, sorry that is not, that is a p naught sine omega t in the first mode generalized force. Same force I will calculate the uh, for the mode 2 p2, that is also coming out to be same p naught sine omega t. So now I have the properties of this, like m and q and double dot t, k and q and t is equal to p and t. So I have two equation, m1 q1 double dot t, k1 q1t p12. One equation this, another equation is this m2 q2 dot t, k2 q2t p2t. These two equation I have. So I can calculate the q1 and q2 corresponding to e by one by one. Okay. So let us go for the first equation. So for the first equation, let us remove this. Okay, so for first or that is the m1 q1 k1 q1 p1t, and p1t was the p naught sine omega t. Now you remember, if you remember, if I have a equation, I had a equation in the single degree of freedom system, in the single degree of freedom system, m u double dot ku is equal to p naught sine omega t. So what was the steady state response? That was the ut is equal to p naught by k 1 over 1 minus omega by omega n square into sine omega t. That was the steady state response from the single degree of freedom system. If you have read in the, if you have read in the first part, in the single degree of freedom system. So for the same here thing here, p naught is replaced by this p naught, k is replaced by the k1, omega n we know, omega we know, sine omega t is same. So the in this the response q1, this is q1t become as a p naught k1 into 1 minus 1 minus omega by omega n square sine omega t. So this is the response as we get in the single degree of freedom system, but the parameters are changed. Like for the first mode, the k replaces the k1. Okay, and here if I write this term, let us say this is c 1 over 1 minus omega by omega 1 square. So this equation, and k1 is what was the k1? That was a 0.586 k. So if I write this, so that become as a p naught 0.586 k c1 sine omega t. Okay. So now this is the response for the first degree of first mode. Now I need to determine the response for the second mode. Now these are the dynamic response. Now we need to determine also the overall response of first degree of freedom, second degree of freedom, and that will determine the next slide. So first let us determine the for the second mode. For the second mode, same procedure, only the M1, K1 and P1 are replaced with the M2, K2 and P2. Okay, M2, Q2 and K2, Q2 and P2T is equal to P naught sin omega t, and same type of solution is coming out to be this. Q2 is P naught by K2 into 1 minus 1 upon 1 minus omega by omega 2 square sin omega t. And this term also here, if I, for the simplification, like again writing the these terms, I will write it here as a C2. Okay, so this term becomes Q2 is equal to P naught 3.41 because the K2 was the 3.41 K C2 sin omega t. So now these are the modal responses Q1 and Q2. Now we determine the overall response. So for this modal responses, U1 can be determined phi 1 Q1 and U2 can be determined the phi 2 Q2. So U1, this is also the response corresponding to first degree of freedom. First mode, and this is also second mode. So the U1 is your degree of freedom, like the your mode was the 0.7071 Q1. So that would become as a U11, U21 become as a 0.707 Q1 and Q1. That is the Q1 corresponding to the, that is the U1 correspond like the U1 corresponding to 0.707. Sorry, we lost the internet. Okay, sorry for the inconvenience, like we lost the internet. So after getting the u1 and u2, same for the mod 2, mod 2 you can calculate the u12 and the u22, which will be coming out to be minus 0.7071 multiplied with the q2. Okay, so here we find out the u1 and multiplying with this q1, and the q1 was the p 0.586 c1 sin omega t. And if we resolve this equation, we will able to find out the u1 is the p 0 by k 1.206 1.706 c1 sin omega t. Okay, and the u2, if we determine u1 to u22, then that would coming out to be minus 0.7071 p naught 3.41 k c2 sin omega t is equal to p naught by k minus 0.207 and 0.293 c2. So that is coming out to be after the rearranging the terms. So after getting u1 and u2, we can find out the overall response, like for the what is the response in the degree of freedom 1 and what's the response in the degree of freedom 2. So for the degree of freedom 1, u1t, that will be the u11 plus u12, like due to first mode due to second mode. And for u2t, that would be the u21 plus u22. Okay, so same things we are following for the first story. u1t is the, like we are adding this, like this term 1.206 and the 0.207 c1 c2. So this is the response of the first story. And for the second story, this is u2 p naught by k 1.706 c1 plus 2.93 c2 sin omega t. Okay, so these are the responses for the u1 and u2 corresponding to the first and second story. So this was our second question corresponding to the determine the displacement for the first story and the second story. Now we are going to the finding out the equation of the like the base shear and the movements for this same question. Like in the another question, we are using the same, like the figure shows the shear frame and the floor mass structure. The structure is subjected to the horizontal force p naught sin omega t, like whatever we discussed in the earlier, p naught sin omega t. So derive the equation for the stories here, considering the steady state displacement only by two method. Like we can find out the shear by the two method, directly from the displacement or the equivalent static. Okay. Now for this, we need mode shapes first thing, modal frequencies, mass matrix, so the and the displacement q1 q2 u1 ut u1 t u2t. So these all things I have we have calculated in the previous question. So we will go further with this direct calculating the shear force. So for this, first let us summarize the whatever properties we need to from the previous questions. So we need to previous question 5 and 5 2 modes we have calculated, and the displacement in the both the modes, in the first mode and in the second mode. Okay, so for the part A, we need to determine the displacement from the base shear from the displacement. So for the displacement shear, like let us, I will discuss this with the, let us we have displacement at irrespective of modes, like I am discussing simple, like displacement at u1 u2. So what will be the shear force in this? That will be the force will be the u1 into k1, the stiffness k1 into u1 minus u naught. U naught is the displacement of this u naught. And same for the second story, that will be the k into u2 minus u naught shear force. So u naught is 0, so that would be k into u1, and that is the k into u2. and plus also that will be add, like this is the force in the particular story. Okay, so for the displacement method, so vjn can coming out to be k into ujn. J is the story number and n is the mode, like corresponding to the first mode. Like let us support corresponding to the first mode, vj1 is the k into uj1 minus uj minus 1 comma 1. So j minus, so for the first story you can write it as a u1 1 minus uj u1 minus 0 is a u0 and so that is 0. So u11 is, what is u11? We get this u11. Okay, same for the second mode. Like in the, like for the, we have four shear. In the four forces you can calculate, and then we can calculate the shear forces. So for the we go with the one by one. For the first mode, v11 is coming out to be k u11 minus u01. So that is the k u11. So that is a 1.2. So that is the stiffness, like the, what is your u11? U11 is the 1.2 something p naught by k into c1 sine omega t. And if I multiply with this k, so that cancel out, that is 1.206 p naught c1 sine omega t. Same for the second story in which k into u21 minus u11. So that is the, k will be cancel out, and if you put the u21 and u11 value from the previous slide, so that is coming out to be, so in which the u21 was the 1.706 p naught by k into c1 sine omega t. So that is the v21. So if you will find out, that is coming out to be zero point 0.5 p naught c1 sine omega t. Now for the second mode, v12 same, like in this, like the mode is changing. So u12 minus u02, this one with the 0. In this, that was the 0. So u12 was the minus 0.207 p naught by k c2 sine omega t. So k is cancelled out. Okay. For the same, for the second story, second mode, that is coming out to be zero point 0.5 p naught c2 sine omega t. So now we need to combine these shear forces. So the total shear force in the first story, that would be the V1 is equal to V11 plus V12 in the first story. That is that this one and this one, that will be added. So that is coming out to be 1.207 C1 minus 0.207 C2. Okay. So P naught sine omega t. Now for the V2 total response, that is V21 plus V22, that is zero point 0.5 P naught C1 sine omega 2, like this one, V1 to this one, and this one. So that will zero point 0.5 is out of the column, out of the bracket. So that is zero point 0.5 C1 plus C2 P naught sine omega 2. So that would be V2, not V1. Okay. So this is the total response. Now we can determine the, to the equivalent static force, and then check whether our answer is like matching or not with the other different method. So with the by equivalent static method, we can determine the, for the equivalent static method, like as you know, like force, what is the force by Newton's law? Mass time the acceleration. Okay, so mass time the acceleration, or you can acceleration, and acceleration, if I know the displacement, so acceleration will be the omega square in time the displacement. So that is the omega square into displacement u. Okay, so that will be the omega square mass, and u can be written as a phi time q. So this is our static static force at the degree of freedom for which mode, that is the, like for the first mode, that is the phi 11 q1. This way we can determine. So this is the omega n square mj phi j n q1t. So first we need to determine the equivalent static force. So for this first mode, we need to determine the f11, that will be the omega 1 square m1 phi 11 q1t. So omega 1 square we know, omega 1 square, and m1 we know, mass and 511 and the q1. So if I know that like omega 1 was the omega 1 square was the 2 minus square root by k by m, and omega 2 square was the 2 plus under root 2 k by m. Okay, and the mass you know m for the m1, and m2 was the m by 2. 511 is 0.707, 521 that is 1, 512 that is minus 0.707, 522 that is 1, and what left? Q1 that was the P naught by 0.586 K C1 sin omega t. Q2 was the P naught 3.41 K C2 sin omega t. Okay, so these are the things we need to put in this equation. So for the omega 1 we know 2 minus under root 2 k by m, mass m1 is m, and pi 1 is the 0.707, that is q1. And if you solve this is the f11 equivalent static force in the first degree of freedom in the first mode. Now f21, in which we need to only change the mode, because only the modes are corresponding to the second degree of freedom, and all other things will remain same, like mode shape, model frequency, because it is corresponding to the first mode, mass q1t. Okay, so if you will put, and that will also change, that will become m2, because this is corresponding to the mass second degree of freedom. So that if you put, that will come as a 2 minus under root 2 k by m, m by 2, this is the 1, this is the q1. And if you will do this, so that is coming out to be zero point 0.5 p naught c1 sin omega 2. Okay, now coming out to be second mode. So in this f12, like this will change, this will become omega 2, that is corresponding to the first mode m1, sorry, first degree of freedom, that is the first degree of freedom first mode, a second mode, and that is the model response of the second mode. And if you will put this is the omega 2 square is given 2 plus under root 2 k by m, mass, mod shape, and the p naught by 3.141, that is c2 sin omega 2, and that is coming out to be 0.707 p naught c2 sin omega 2. And f22, that will be same, omega 2 square m2 by 22 q2t. And if you will put this equation, that is coming out to be this same. So now you have the is equivalent static force, like this one is the f11, this is f21, same for the, this is f12, this is f22. So shear force in this, that will be the v21 and v11. So v21 would be the f21, v1 would be the v11 would be the f21 plus f11. Okay, same for the second mode. So the story is here. So v11 would be the whatever I have discussed, f11, f21. So if I add these things, so if I add these things, so that will become as a f11 this, f2 this is f11, this is f2, that is 1.207 p naught c1 sin omega 2 omega t, and v21 is the f21 zero point 0.5 p naught c1 sin omega t. This is for the first mode. And for the second mode, if you determine, that would be the same, like let us say this is f22, this is f12, so that will be the v22, and that will be the v12. Okay, so v12 would be the f12 plus f22, and v22 would be the f22. Okay, so I have put the value of f12 and f22. So v22 is coming out to be up to 2.5 c2 omega t. So the combined shear would be the, for the first story, that would be the v 1 1 plus B 1 2, and for the second story that would be the V 2 1 plus V 2 2. Okay, so this way, if we combine the added to the force, we get this. Same for the second story, that is. And if you compare this from the previous one, these are coming same. Like by the both the methods provide same results. Okay, so that depend on you which method you want to use, because that doesn't affect your results. Okay, now come to the last question of this, in which we are using a different kind of force. Initially that was the sinusoidal force at the top, now in which we are applying the impulsive force at the second floor, and that force is P naught delta T, and where P naught is given as a 89 kilonewton. Okay, so for this we also need to first determine the mass matrix and the stiffness matrix. So for this we will directly, you can do it by yourself, I will provide the directly the answer for the mass matrix and the stiffness matrix. So this is the degree of freedom 1 2 3. Okay, so this is the mass matrix 100,010,000.5 m. This is the stiffness matrix, that is can be calculated as a k1 plus k2 minus k2 0 minus k2 k2 plus k3 minus k3 0 minus k3 and k3. Okay, like simply this, k1 plus k2 minus k2 0 minus k2 k2 plus k3 minus k3 k3 k3. Okay, this is the stiffness matrix how you can calculate. And the eigenvalue and eigenvector are directly I have calculated. Lambda 1, lambda 2, lambda 3 are 2 minus under root 3 k by m. Lambda 2 is 2 into k by m. Lambda 3 is the 2 plus square root of 3 k by m. And if I will calculate by k is given as a 57,000 kilonewton meter, or I can convert it into the 57 into 10 raised to power 6 Newton per meter. And the mass is given to you 4500 kilograms. Okay, now put the value of k and m and determine the omega 1 and omega 2 3. So that is coming out to, omega 1 is coming out to be 18.42, omega 2 is 15.33 50, and omega 3 is 68.75 radian per second. So now after getting this omega 1 omega 2 omega 3, I need to calculate the mode shapes. So the eigenvector in the mode shapes, so these are I have calculated directly, you can do it by yourself. So that omega phi 1 is coming out to 0.5 0.861 minus 101 0.5 0.861. Okay, so these are the mode shapes. Now we need to calculate the generalized property for the uh, equation of the mn qn double dot t plus kn qn double dot t is equal to pnt. So we have three mn, m1, m2, m3, k1, k2, k3, p1, p2, p3. So the m1 can be calculated as phi 1 transpose m phi 1. So if you will put the values of the this one and this one, phi 1, phi 1 transpose phi, and this is m, that is coming out to 1.5 m, and further it is coming out to be 67,500 kilogram. Similarly for m1, m2 and m3, if you will calculate it, so that would be the m2, that would be the m3. Okay, you will be able to find out the m1 m2 m3. Now determine the k1 k2 k3, so in which only the thing will be changed the this matrix. So after calculating the k1, this is your k1, so k1 k2 and k3, these are my k1 k2 k3 generalized. Now the generalized force. Okay, so the generalized force is given as a pt is given as a 0 p naught delta t, because it is applied on the second floor. So for the impulsive force, what is my uh, response, that is the ut is equal to I by m omega n sin omega t. So that is the I is the p naught become, that is the given us, and m omega n. So if we could calculate the response, 5 1t pt is coming out to be 0.5 p naught delta t. And if we will multiply this with this, so this becomes a 0.86 p naught delta t, so that is become a 77 delta t kiloliter for the unit impulse. Okay, same for the p2t, that is become 0 because that is multiplied with this one, that thing will be equal to 0. And for the p3, that is become negative because this is negative. Okay, that is 77 delta t. Okay, now you will generalize the equation of motion for the multi-degree of freedom system, that is mn qn double dot t kn qn is equal to pn. And for the solution of the impulsive loading, that is xt is the I by omega n sin omega t. So for the solution of the above equation, q1 is given for the first, if you will look at the uh, first mode. So your first mode for the given the model response q1 is equal to I1 or the p1 by m1 omega 1 sin omega n t. And for the second mode, that will be the p2 by m2 omega 2 sin omega 2. And q3 will be the p3 m3 omega 3 sin omega 3 t. Okay, so if you will put the q1 q2 q3, like p1 m1 and q1 we have calculated earlier, that is 67,500 in the earlier in the all the cases. And the omega 1 is the 18.42, p1 is given as a 77,000 as we have given in the, that is a Newton. Okay, so if you will calculate, that is coming out to be 0.0619 sin omega 1 tm in the meter, or 62 sin omega 1 t mm for the q2, because that is 0 because of q2 is 0. And for q3, that is become the same, but in this the m3 and the omega 3 is different. So that is omega 3 is the 67.75, so that is coming out to be so 90. So if you combine the model response, displacement vector of the u can be expressed as a q1 5 1t, q2 5 2t, q3 5t. So that will be 0 because q2 is 0. So multiply with this, like the vector, like the point 0.5 minus 0.86, that is a plus 1. And for the 5 3, that is point 0.5 minus 0.86, 1 q1 q2. Okay, so this is the mod 1, that is this is the model vector 3 and the q3, and this is the combined model response. Okay, so this is the last, that is the last question I have discussed. So these all four questions are related to the force vibration, or the force vibration response of the multi degree of freedom system, in which we have discussed the various cases for the calculating the displacement and the shear. So in the next lecture, we will discuss the the multiple problems calculating the seismic response of the multi degree of freedom system. So if you have any doubt, you can ask me here, or if not, you can ask me this doubt from the go from the discussion form. So you can ask me there, so that I can give your answers from there. Okay, so thank you. I am concluding this session here.